So in today's lecture, we'll be seeing DFT as a linear transformation. That is, we can write, for instance, linear transformation means consider x is a vector and we have to get some vector y after performing some transformation. So this A is known as the transformation matrix. So we had learned the expression for DFT and IDFT as summation of some terms. Now we are converting that into an easier way of solving it, that is using matrix multiplications. So we'll see how that is being done. Let us assume that, so this is, we have just converted the actual expression for DFT, that is actual expression for DFT was summation x of n e raised to minus j 2 pi nk by n. Similarly, IDFT. So what we did is, instead of e raised to j, we substituted another term wn, that is known as the twiddle factor, and it is represented by e raised to minus j 2 pi by n, or it is known as twiddle factor is also known as nth root of unity. So this is an important term, the twiddle factor. It will come always for the later chapters also, twiddle factor. So Wn is e raised to minus j 2 pi by n. So we are just substituted for e raised to j the actual expression for DFT and IDFT here. Next, let us define a matrix of this sort. Wn is equal to n by n DFT matrix. This is W, capital W, Wn, that bold letter is representing a matrix, and the size of this matrix is n by n. If you are told to find an n DFT matrix, n DFT, you have to, your DFT matrix size will be equal to n by n. So what are the elements in this particular matrix? So here each of the element in the matrix is equal to Wn raised to nk, where Wn is e raised to minus j 2 pi by n. So how do you find the element? So it is not represented explicitly here, but here I'll write for understanding, I'll just write on top n equal to 0, n equal to 1, 2, n equal to n minus 1. Similarly, this side I'll write k is equal to 0, k equal to 1, to k equal to n minus 1. So now what does this element mean? The first row, first column, that is equivalent to Wn raised to n, and k is 0 here, so it will be 1. Similarly everywhere. So for n by n DFT matrix, the first row and first column will always be equal to 1 due to this k equal to 0 or n equal to 0, or here k equal to 0 or n equal to 1, etc., etc. Now let us go to the third row, that is k equal to 2. That is third row I'm going. Let us see how we are getting that value. That is, the first element will be equal to Wn raised to nk, so that is 1, because n equal to 0. The second one, Wn raised to n is equal to 1, k equal to 2. So that is how you get Wn square. The third element, that is for n equal to 2. So that is Wn raised to 2, k equal to 2, and n equal to 2. So that is Wn raised to 4. Similarly, the last element is equal to Wn raised to k is 2 and n is equal to n minus 1. That is how we get element. Likewise, each of the element in the DFT matrix is filled. So now let us see this particular thing, that is an n by 1 signal vector. So here, before we used to give signals as a single as a single element. Here we are taking all the samples from x0 to x of n minus 1 and putting it in a column vector. That is n by 1. We call it as a n by 1 signal vector. It's a column vector of size n by 1, n rows, 1 column. So we put it like this. And bold letter means it's a vector. Now capital means capital is transformed DFT, transformed version of your time signal. That is your DFT signal. So that will be, instead of x of k, you have n samples. That is x0 to capital X0 to capital X of n minus 1. All I did is I just took all the samples and put it in a column vector, and it is the DFT transformed signal vector. Now what we can see is we can represent our DFT, comparing it with the actual expression of DFTs, or with this particular expression. If you look at these two expressions, it is same as. Now if you want to do it using this equation, find the DFT, you have to substitute for k equal to 0 and find the summation. You will get one answer. K x equal to 0, x equal to 1, k x of 1 means k equal to 1. That also you substitute, you will get another. So you have to do sample by sample each value. Here the same thing we can do if you are putting the signals in a single column and then multiplying. That is using the DFT matrix. You can see it for yourself. If you want, you can just substitute, expand and compare it with the actual expression for DFT and see that you will get the same answer. But advantage is you are finding the full n DFT in a single go instead of substituting for each values of k and doing it. Similarly, comparing it with your expression for this one, w n raised to nk. So what is the meaning of e raised to j theta and conjugate of e raised to j theta? That is wn is what? Wn is equal to e raised to minus j 2 pi by n. So what is wn conjugate? It will be equal to e raised to j 2 pi by n. Now I can represent this particular expression as what? I can represent this thing as 1 by n summation k equal to 0 to n minus 1 x of k w n conjugate of nk. That is the same thing. So that way I will get this particular answer. That is the matrix transformation form of finding your IDFTs. That is, this particular thing is known as conjugate transpose of a matrix. Conjugate transpose means you are taking the conjugate of each element and then transposing the whole DFT matrix. That is known as conjugate transpose. So that is this particular thing. Now, so this much is the direct straightforward way in which you can get the solution for DFT and IDFT. Now we'll see a relation between or a property of the DFT matrix. So from 2.6, this particular expression, I can get what is x of n, small x of n, that is the time domain signal vector. That is equal to wn inverse x of n. So now if I compare it with this particular expression, both x of n, here also x of n, here also x of n. So here what can I do? I can see that wn inverse is same as 1 by n wn conjugate. Just comparing the two expressions. That is how I get this one. Wn into wn conjugate. Wn is equal to wn inverse is equal to 1 by n wn conjugate. Now if I take it to the other side, what will I get? That is Wn into Wn conjugate is equal to, so this is a n by n matrix. This is a n by n matrix because both are n by n. When you multiply also, you'll get a n by n matrix. So it will not be equal to just n. It will be a n into in, where in is a n by n identity matrix. Identity matrix. Because identity means it will have only elements in the diagonal and it will be equal to 1. Rest all it will be zeros. That is known as an identity matrix. So this is your expression for this. This is a relation or important property of your DFT matrix. But what do you understand by that? So in matrix algebra, you would have learned that linear algebra. You would have learned that a matrix is orthogonal if Wn into Wn transpose is equal to I. That is the property of an orthogonal matrix. Here, it is the elements are complex numbers, and here instead of transpose, what I took is conjugate transpose. So it is conjugate transpose, and only difference, instead of I we have a scaled I, that is n into I. So since the elements in this thing is a complex number, instead of orthogonality it is equivalent. If the elements in Wn were real numbers, it is known as an orthogonal matrix. But here the elements will always be a complex number because it is e raised to j, that is cos theta plus j sin theta. So Wn is a complex matrix. So I can say that instead of orthogonal, it is known as unitary matrix. That is equivalent of orthogonal in the complex domain. It is known as unitary matrix. Now we'll see the computational complexity of this particular matrix or finding the DFTs. Here, if you look at this expression 2.6, so x of n is of size n by 1 is equal to Wn, which is of size n by n, and small x of n is of size n by 1. So Wn, let us take a single row and single column of x of n. So what is the computational complexity of finding a single element? This element, first element, that is I have to multiply. So basically this matrix multiplication, the computational complexity, that is this row, first row into the column of xn. So how many multiplications are there? N multiplications. And there are summations. First element into first element plus second element into second element plus. So it will be n minus 1 additions. For finding, so this much is a computational complexity for finding a single element or a single sample of the DFT. Likewise, how many samples are there? Likewise, n samples we have to find. So your total actual computational complexity is n square multiplications and n into n minus 1 additions. So that is the actual complexity for finding an endpoint DFT. Now there is a property, two properties of the Tudel factor, that is Wn raised to k plus n is equal to Wn raised to k, and symmetry property is Wn raised to k plus n by 2 is equal to minus Wn raised to k. So this thing I'll just give a basic idea what is the meaning of this one. That is, you can prove this. So they might ask you to prove this. I'll just show you how to show that this is a valid answer. That is Wn is e raised to minus j 2 pi by n. So that is e raised to minus j 2 pi by n. So plus n means, so 2 raised to minus j 2 pi by n. So k, instead of Wn raised to k, will be e raised to minus j 2 pi by n k. So now let me take Wn raised to k plus n. So that is equal to W e raised to j 2 pi by n into k plus n. That is equal to k into e raised to minus j 2 pi. Now what is the value for this one? It will be equal to 1. Thus we are going to get the same answer. That is Wn raised to k, n raised to k, and Wn raised to k plus n. Both will have the same answer. Thus similarly, when you substitute same method, you can find out the solve the symmetry property for twiddle factor. Next, we'll do a simple problem on DFT. That is, given an expression like this, DFT of x of n is equal to 0, 1, 2, 3. Here, there is nothing is asked in the question, like you have to find an 8-point DFT or anything. If you are asked to find out an 8-point DFT, you would have to have padded with 4 zeros and then do the question. Here, nothing is asked. So, obviously, you have to go with the 4-point DFT because that is the size of the actual signal. So here first we will be doing using the matrix multiplication method. The other method is summation, opening the summation. Here we will just do the matrix multiplication method. So here first our aim will be to calculate W4, that is the capital, your bold letter W4, that is your 4 by 4 DFT matrix. 4 by 4 DFT matrix. So here what you are going to do is you have to just substitute the initial step. I'll go step by step. That is, if you look into your DFT matrix, this particular thing, that is, your first rows and columns will always be equal to 1. So there is no question in that. Row and column will be equal to 1. Next, it will be Wn raised to nk, Wn raised to your each element will be equal to Wn raised to nk form. So here it will be W4 raised to 1, W4 square, 4 cube, again 4 square, 4 raised to 4, W4 raised to 6, W4 raised to 3, 4 raised to 6, and W4 raised to 9. So that will be your DFT matrix. This is, you can just compare with this particular standard form and you will get this answer. Next, you might think that you have to find each and every element in this matrix first before getting your answer. But the advantage is, due to the periodicity property and your symmetry property, you can reduce the computational complexity. That is, if you look here, you can write, what can you write about W4 raised to 3? W4 raised to 3, that is this element. W4 raised to 3 can be written as W4 raised to 1 plus 2. Now have a look at your symmetry property. Just written like this. So that is n by 2, capital N by 2 is 2. That is this 2 plus 1. So according to symmetry property, what should be your answer? Because this is equivalent to doing W4 raised to 1. Similarly, what is W4 raised to 9? So that I can write it as W4 raised to 8, or 1 plus 8. So that, let us look at the periodicity property. So periodicity property n, capital N, 2n, 3n, etc. that is same thing because of the period. Same period repeats. So 2n, capital N, capital 2n, capital 3n, 4n, etc. is the same thing. So here this is equal to capital 2 into capital N. So that is this one. So here have a look at your periodicity property. I can write it as W4 raised to 1 plus 8 is same as W4 raised to 1. And similarly, what about W4 raised to 6? W4 raised to 6, I can write it as W4 raised to 2 plus 4. So this is your direct periodicity property if you look at this one. That is same as W4 square. So that way you don't have to find all these elements. So these are intuitive. After you do, you will know which all you can apply periodicity property and which all you can use symmetry property. So now after doing all this, after modifying, so I can modify my DFT matrix and apply. So my final DFT matrix will be something like this after modifications. So it will be W4. So W4 will be 1, 1, 1, 1, 1, 1, 1, W4 raised to 1, W4 square, and W4 cube we got it as minus W4 raised to 1, minus W4 raised to 1. Next W4 square, and what is W4 raised to 4? W4 raised to 4 is equal to W of 4 raised to 0 plus 4. So what can you say about that one? W4 raised to 0. Again, look at the periodicity property. So it is same as W4 raised to 0. So that is 1. We'll write it as W4 raised to 0. Then W4 raised to 6 is equivalent to W4 square. Next, W4 raised to 3. We have got it as minus W4 raised to 1. W4 raised to 6, we got it as W4 square. And what is W4 raised to 9? W4 raised to 9 is W4 raised to 1. So this is our final DFT matrix. Now we have to find the elements of this DFT matrix. So how do you do that? So we know that Wn small each element Wn is equal to e raised to minus j 2 pi by n. So what is for instance W4 square? So W4 square will be e raised to minus j 2 pi into 2 by n is equal to 4 here, and you write it in terms of cos theta minus j sin theta form and find the answer. You will get a complex number, and then so each of this DFT matrix you have to find each element like this, and you have to populate the DFT matrix. After that, direct, you just have to put your actual answer, that is x of n will be equal to your W4. So I'll call this the x of 4. That is your answer. Capital X of 4 is equal to W4, and what is x of n? X of 4, small x of 4. Where small x of 4 is equal to, we put it in a column vector 0, 1, 2, 3. That is your x of 4, and you can find the answer, and that is given here. So you must cross check this one and verify the answer. So this is what we have studied today. That is, you can find the DFT using basic matrix multiplications instead of your sample by sample method, that is opening the summation and doing. And this would be the way your computer processes DFTs, that is matrix multiplications.